Start as soon as we can because I think it's just wrong time. But I must thank Emilian and Sasha and of course Vernon for the invitation to come this time. Some 7 years ago there was a conference in Edinburgh on hydroelastic waves, which I didn't get to because I was in the process of moving from Hamilton in New Zealand to what is now my home in Adelaide. I'm an old South Australian, but the New Zealanders never knew that. I was a long time in New Zealand. But also I don't like flying very much. I'm reminded of the story, I think, a British lady who said, if God had meant us to fly, why would he given us the railways? So I'm a little bit like that. I don't like flying long distance, but I'm very pleased to be here in person, rather than to be here remotely as last time in Edinburgh. So my thanks to the organisers. I had hoped Roger Grimshaw might join us, but he's moving house. So at that time, in June, 7 years ago, I was moving house. And this time we have non-linear, but Roger is moving house. In the old days, we were the two Rogers at the Applied Math conferences in Australia. There were the two Ronnies. You remember the two Ronnies? I'm sure, some of you at least. All right, well, without further ado, it's Pat to speak to us. Pat I knew as a colleague at a distance, but I'm happy to have met her at last. Thank you, Pat.
Thank you. Is the microphone on?
Oh, yes.
Yep, thank you. Well, thank you. I'm Pat Langhorne. I'm from the University of Otago in the South Island of New Zealand. And the talk that I'm giving, the lead author is another Pat Wongpan. He's a PhD student of mine. And Ken Hughes was a past master student, Inga Smith's a colleague, so we're very happy to be able to present you this work. We already want to change the title and call it Brine Convection Temperature Fluctuations and Permeability in Thick Winter Sea Ice. So it's a bit of a change from the talks we've been hearing largely so far over the course of this workshop. I want to start, since it's just after lunch, by giving you the take-home messages. So I'm talking about thick sea ice, land-fast sea ice, and what we're interested in is how the movement of brine produces fluctuations in temperature that we are attributing to brine convection in a layer. Now, these things happen when the ice is warm, and we've got some measurements that will say that these are going to be happening at temperatures above -3. When I say a temperature fluctuation, what I mean is something that's taking place over less than 12 hours. And the temperature fluctuations we've got in our measurements are of the order of 10 millikelvin, so they're not big. So our take-home messages are that there are observed temperature fluctuations of the order of 10 millikelvin taking place due to brine convection, and we're going to use that as a proxy for brine convection. These fluctuations take place within about 100 millimeters, 0.1 meter of the ice-ocean interface, and they take place largely when the temperature is above -3. They take place sporadically, and they take place all the way through winter when the sea ice is growing. And we have about 12 months of data from 3 different years. And the last point is due to our own little particular interest, and that's to do with the difference between columnar sea ice and incorporated platelet ice. And I'll say a little bit more. These are 2 different ice structures, and what we find is that the permeability doesn't depend on the particulars of the ice structure. So let's have a look at what's going on here. Well, we heard in workshop 2 from Gray Wooster that sea ice is an interface. Sea ice is usually 1 to 2 meters thick. It's an interface between the much larger atmosphere and the much larger ocean. And in the simplest form, we can think of sea ice growth just in terms of the fluxes to the atmosphere, FA, and flux to or from the ocean, F0. So that's the very simplest way we can think about this. But not all interfaces are equal. So Pat has picked out two different types of interface that we might have here. The one on the left is called incorporated platelet ice, and it's what we get when we're next to an ice shelf. I'll say a wee bit more about how it forms. And then the one in the middle is columnar sea ice. And so what we see is sketches of the two different modes of formation, photographs of the ice-water interface, and photographs of the crystal structure at the bottom of the ice. So let's just take a closer look at what we might see if we look at the interface. This is just a pretty of some platelet ice. Us platelet ice aficionados cannot resist putting in some pretty pictures. Anyway, so let's take a look at the ice-water interface. So here's the lead author of this presentation, taking the plunge beneath the ice-water interface at Davis Station in Antarctica. And if he had not been concentrating on the blood supply to his extremities, this is what he might have seen when he got underwater. So this is an ice-water interface of columnar sea ice. I think there's a few things to note. First of all, it is relatively flat. So you might be able to see some little undulations here. They're kind of sub-millimeter scale. So that's the first thing. Fairly flat interface for columnar sea ice. Second thing to notice is that it's a place where there is lots of life. So the brown is algae, and the little black squiggly things are little black squiggly things eating the algae. And these are about 2 millimeters in length. So that's the interface, ice-water interface of columnar sea ice. The ice-water interface of platelet ice is quite different. Much bigger crystals here. We're now on the centimeter scale. And the reason for that is that the mode of formation is slightly different. I showed this in the previous, there we go, little movie here. The thing we're looking at are the ice crystals in the water. Once again, some biology. There's never no biology there. Please ignore that. What you're focusing on are these little sparkles. These are ice crystals coming up underneath the sea ice, having come from the ice shelf and then freezing in place at that location. And they collect under the sea ice, and the result is that the crystal structure is different between columnar and platelet ice. So here are thin sections through columnar on the left and incorporated platelet ice on the right. Not really interested in the crystal structure, except that the brine inclusions, which we are interested in, are largely situated at the grain boundaries. So the crystal structure does tell us something about where the brine inclusions are. So just looking at this, you can see for the columnar ice, our crystals are large and going in columns, hence the name. In platelet ice, the crystals are all higgledy-piggledy and form a jumble, and that jumble is reflected in what the brine structures look like within the sea ice. So on our left is columnar ice. You can see there are long cylindrical inclusions. These are largely separated by about 0.5 millimeter from each other, and so their dimensions are less than 0.1 of a millimeter. So this is columnar sea ice. On the right-hand side, we have incorporated platelet ice, and you can see once again, just like the crystal structure, the brine pocket structure is rather higgledy-piggledy. And then the biggest brine drainage features in sea ice are these fellas here. So this is a brine drainage channel, and Elizabeth showed us some nice pictures of brine drainage channels yesterday. This is a brine drainage channel once we've sampled it, and the brine in that channel has refrozen because we've sampled this, made this section at low temperatures at -20. So the brine that was there becomes small ice crystals. So we have this assortment of brine drainage features. It's a complex system, and thanks to the work of lots of people, some of whom are in the audience, we may treat this as a continuum. And think of sea ice as a mushy layer. So in other words, it's a two-phase, two-component reactive porous medium where we can define a bulk temperature, a bulk salinity, some solid fraction, and then think about the fluid movement in terms of a Darcy velocity. So this is an experiment that Pat's picked out from the work of Middleton et al. So showing this mushy interface growing. So we're going to be thinking about the permeability. So the number of questions we're going to be asking are, can we be sure that the fluctuations we're going to look at in temperature are because of brine? If so, how can we use these temperature fluctuations to tell us something about the sea ice permeability? And for that, we'll need mushy layer theory. So let me just say a few words about the permeability of sea ice. Pat's picked this out again off the web. It's a picture showing some dye penetrating into, well, as contrast, pure ice on the left and sea ice on the right. Our Darcy velocity is going to depend on the permeability, which here we call pi, and it depends on the pressure difference across the layer. And we're going to be thinking in terms of a layer at the base of the sea ice that will follow Rhys-Jones and Worcester and call H minus Z, where H is the ice thickness and Z is the position of interest. So the permeability of sea ice is much bigger than the permeability of pure ice, which is why all these critters like sea ice so much. It's a place where nutrients can reach them when they're inside the ice. And sea ice permeability is either very variable or it's very purely known, one or the other. There's a whole range of 10 to the 6 that you can have, 10 to the 6 meters squared for the permeabilities. It goes, measured values go from 10 to the minus 13 to 10 to the minus 7. So that's where we're aiming to have our measurements sit. Gives us plenty of room. So, and as I said, permeability in sea ice is one of the reasons why algae and other animals just love to be there. So how are we going to estimate this in thick growing sea ice in midwinter? Well, we need to think about some of the fundamentals of convection in sea ice, which takes us to the mushy layer theory. So here's a little schematic of our ice slab, Z being measured to our position of interest, and H is the thickness of the ice. We can think of a packet of fluid, and that will have a buoyant potential energy that is dependent on the fact that that packet of fluid might be more saline than the fluid below it. And so that's a rough expression for the buoyant potential energy. We can compare that with the energy that would be dissipated. And that energy that would be dissipated by our packet moving from here to here is given in terms of the Darcy flow, which we are calling W, the permeability, that distance, and the size of the packet. Now, I should say, first of all, this is not my work. This is David and Gray's work, putting this in this form. Now, in this, thinking about it in this way, there are two time scales. One is the time scale that it would take for this packet to move down, and that's given by h minus z divided by the velocity. And the other characteristic time scale is the time at which that would be required in order for the heat to diffuse and therefore for the buoyancy to be lost. And so you're only going to get buoyant convection if this time is less than that time. Or we can think of it as convection will take place only if the potential energy divided by the dissipation is bigger than 1, in which case we can rewrite things in terms of a Rayleigh number. So here's the expression from the Rayleigh number, written as Worcester and Rhys-Jones would have written it, in terms of the difference in salinity from the ice-water interface up to our position of interest. That's the position of interest, the distance it is above the ice-water interface, the local permeability at that position. These are thermal and diffusivities of heat and momentum. And that's the coefficient of saline expansion, haline expansion. So in other words, if our Rayleigh number exceeds a critical value, then convection will take place. The crux is, of course, what's the critical value? And so I'll skip over that very quickly and say it's 10. So how can we measure that? If we look up on the right-hand side here, here we had our thin section. Let's imagine that we've got some temperature sensors in this ice, and these are these red dots, and they're measuring some isotherms. And if there is a brine event and the brine flows, then these isotherms are going to be displaced. And the displacement of the isotherm can be detected by the position, by the temperature sensors. So that's going to be our argument for how we can measure convection from temperature strengths. So here are our temperature strings. They're placed in McMurdo Sound, which is shown in the map here. It's up in this little part of Antarctica there. This is a sketch of the physical situation of our platelet ice. The red dots are the positions of the temperature sensors. I grabbed this off the web. We have temperature sensors in the ice at the moment, and they're almost real time. So in fact, given that I only took that off an hour ago, it's actually going to be telling you the temperature this evening because of the time difference between New Zealand and here. So not only does it give you the temperature, it predicts the temperature. Anyway, so these temperatures are being measured right at the moment, and if you're interested, you can go and look at them on the web. So this is the ice. This is our sketch of what we think the ice does as it grows. So let me just, I have shown this before, but let me just talk about it again. This plot shows time going left to right, and in this direction we have ice thickness. Down at the bottom we have the heat fluxes, and F naught is the heat flux to the ocean that we saw in the previous equation for determining what the ice growth would be. So when the ice first forms in McMurdo Sound, it will grow with a nice solid columnar interface. So in this region here, we have columnar growth. There comes a point in the winter when the heat flux effectively becomes negative. That means the heat is not flowing from the ocean to the ice, it's flowing from the ice to the ocean. And in these situations, we get incorporated platelet ice. So with our temperature strings through the winter, we're going to sample not just columnar ice, but also incorporated platelet ice. So we're going to be able to sort these two different ice types out from each other. So here are some temperature measurements. These are from 2009. Doesn't really matter. They're plotted with different colors depending on their position. So this is a sketch of the thermistor string. These ones are all in the water. The shaded ones are in the ice. The ice-water interface is plotted at the bottom, so temperature is increasing downwards, just to make it easier to understand what's going on. So where these all converge together, this is the temperature of the ocean, which is constant. And then as the ice grows, as a thermistor as a temperature sensor is engulfed, the sensor temperature moves upwards. Now, if we home in on these, we see that there's not always a smooth change, but we'll see that from time to time there are these peaks in the data. And if we home in on this little section, we can see the fluctuation that I'm going to be talking about. So it's this deviation from a mean through the temperature record that I'm interested in, that we're interested in. So the crux of the matter is to pick out the fluctuations from the mean, and we do that, since we need a robust method, we use the robust LOESS method. And if you're interested, I'm happy to go into it, but the bottom line is it's a nice method for pulling out a mean and then allowing us to see excursions from a smooth signal. So our data are these, so we're interested in these temperature fluctuations, which we're going to say are due to brine motion. T LOESS is our mean temperature, and T is the measurement. And so here's what we get if we plot it all up. I'm sorry, on the projector it comes up in a kind of bile-coloured yellow. It's not quite so bad on the screen, but... All right, so what we've got here. We have time through the winter in this direction, and then depth in the ice in this direction. And what's plotted here as a parameter, shown as the colour, is the temperature fluctuation. So yellow means essentially not much temperature fluctuation, and the blue colours, blues and greens, mean fluctuations in temperature. The red line, the solid red line, is the ice-water interface, and the dotted red line with circles is the -3 degrees C isotherm. So what I want you to take from this plot is that these temperature fluctuations are largely taking place between -1.9, the freezing point, and -3. They're taking place at other times too, but that's largely what's happening. So we're picking out these temperature fluctuations, and we're able to look therefore at the statistics of the fluctuations, because we have at least 3 years of measurements that we've processed, and so we can look at how these temperature fluctuations have changed. So there are two plots here. On the left-hand side, we have plotted the magnitude of the temperature fluctuation against the average temperature. And the thing I want you to note there is that the temperature really has to lie in the range -2 to -3 for us to sense a temperature fluctuation of significant magnitude. On the right-hand side, we are plotting these temperature fluctuations as a function of distance from the interface. And 0 here, I'm sorry, our lines have disappeared. 0 is the ice-ocean interface. So all these measurements to the left are the ocean, and there are not very few fluctuations in the ocean, or they're of small magnitude. And then the fluctuations are largest as you move into the ice. And again, the fluctuations are largest within about 100 millimeters of the interface. Now, we can also ask, if we look at one thermistor, what would we see? So again, Pat's picked out this nice simulation from Middleton, and I'd asked you to think about this. I might just go back. I want you to think about this thermistor here. Initially, it's in the ocean, and then as the ice comes past it, it's being engulfed into the ice. And in a sense, this is what we're plotting here, only in thick Antarctic sea ice in winter. These are the fluctuations that would be seen by this thermistor when it was in the ocean, and they're less than some threshold. When it goes into the ice, they become larger and exceed a threshold. And then when you're a larger distance from the ice-water interface, like up here, then the fluctuations die down again. And we've quantified this in terms of whether the brine convection is on or whether it's off. So at times when there is a big fluctuation, we say it's on, and that's signified by the black bar. And when there isn't a big fluctuation, we say it's off. So it's very simple. And we've put the data in two bins. So essentially what we're saying is there a flow down this brine tube or is there not? And categorizing that as on or off. So here's our plot of whether or not there is a brine drainage event going on. So on the y-axis we have the on percentage of the time, and on this we have distance from the ice-ocean interface. And we've put them in two buckets. We've put them in a warmer than -3 degrees C bucket and a -3 to -5 degrees C bucket. And I think what you can see is that when the ice is warm is when you get the largest values of on percentages. Not surprising, really. So within 0.1 meter of the interface, the fluctuations, temperature fluctuations, are happening for more than 40% of the time. When you move up into the ice a little bit and the temperature is -3 to -5, then these fluctuations might only be happening 10% of the time. There's obviously a lot of scatter in these data, though. All right, so how do we use these ideas to estimate permeability? What we're arguing is that convection is taking place when the local Rayleigh number exceeds its critical value, and we're arguing that when that convection takes place, we see it as a temperature fluctuation. So we need to think about the Rayleigh number. And here is the Rayleigh number written as before. We can rearrange that expression of Worcester and Rees-Jones to give us the permeability. We say that brine convection is taking place when we see a fluctuation, but actually it's a more strict requirement than that. We need convection to be taking place not only at the top thermistor, but also at all of the thermistors underneath it. So we're not measuring a permeability at one position, we're measuring a harmonic mean permeability that is the harmonic mean of the sum of all the layers underneath. So it's a sort of bulk permeability for the whole layer between the thermistor at the top and the ice-water interface. So here's what we claim to be measuring. We are estimating, or I should say estimating, it's not strictly a measurement. Here's our bulk or harmonic mean permeability. That's a bunch of constants, which we will claim we know. So what we have to find is the difference in brine salinity between the ice-water interface and our position of interest. And we need to find that distance between, that gives us the position of the highest temperature measurement that is connected all the way to the bottom. And I can go into more detail if anyone's interested in how we do that. I like this sketch, again from Worcester and Rees-Jones, to try and explain what we've done. What we're doing is, here's H minus Z, the difference from the ice-water interface, plotted as a function of, well, not plotted, sketched as a function of the Rayleigh number. So we might expect a Rayleigh number profile like that. Also plotted is H minus Z as sketched against the Darcy velocity. So what we're doing is we're saying, if we detect a temperature fluctuation here and here and here and here and here, then we say our H minus Z is the position of the highest one. So then what we've done is take all of these measurements, put them all together, so taking the measurements from 2009 and 2010 and 2013, and find a histogram of H minus Zs. And we've plotted that as a function of, well, we've plotted two histograms here. The blue are columnar ice, and the brown are when we have incorporated platelet ice. So that gives us our H minus Z. We also want delta SB. Again, I can go into more detail on how we do that if you're interested. So now that we've got delta SB and we've got H minus Z, we can find pi, and we can plot these as, again, as a distribution. So this is the distribution of permeabilities over that distribution of H minus Zs, of distance from the base of the interface. And the thing we were really interested in was, is the distribution different for columnar ice, which is blue, than it is for incorporated platelet ice? And we'd say, no, it isn't. It's the same. Well, we cannot tell that it is different, actually, is strictly what we can say. So this is making a null hypothesis using Kolmogorov-Smirnov test. The null hypothesis being that the platelet permeability distributions are drawn from two different populations. The test fails to reject that test, which means that we will say that we believe that the permeabilities are the same. Now, our permeabilities are also, you will see, this is plotted on a log plot, so they go from 10 to the minus 10 to 10 to the minus 7, big range. but at least in the same big range that everybody else gets. So, to go to the conclusions, we have used temperature measurements to deduce something about brine convection at the base of thick growing Antarctic sea ice. Now when I say thick, I maybe didn't mention it, I mean 2 meters, 1 to 2 meter thick Antarctic sea ice. Growing in winter, and we've done that over 3 different winters, or at least we've processed the data for 3 different winters. Within 9 centimeters of the interface, where the temperatures are greater than about -3, these fluctuations take place sporadically for over 40% of the time. And then finally, we would say our average permeability for either columnar or incorporated platelet ice is about 10 to the -9 meters squared within this 200 millimeters of the interface. Thank you.
Thank you, Pat. That leaves ample time for questions.
How do you feel about the sea ice uncertainty principle? Where the probe that you put in, does that create a brine channel in itself?
Oh, yes, good question.
Having done this,
No, we have seen evidence in the past of when we think that might have happened. I don't think it's the case for all of these probes. I mean, we're talking now about, we've done this 12, 14 winters.
you're also growing the ice past the probe too, right?
Oh yes, the ice is growing past the probe. Yes, yes. So
We did it, we put it in the summer ice, so.
Oh no! This is cold. This the probes go in usually, apart from the 2009 data when we actually had people winter over, they're usually put in by base staff, and they'll be put in the middle of winter. So they're put in June, and the temperatures are -40. So I think it's fairly unlikely. We do worry about that. That's what we design them with. Thermistor sort of fingers sticking out to the side to try and get the sensor away from the probe. But yes, you're absolutely right, you do have to be awfully careful.
Thank you very much. You spoke a lot about the tiny details, the
Yes.
vertical flows and so on, but suddenly you had a statement which was kind of very different. You said that underwater snowstorms do happen.
Oh,
What,
yeah.
what are these? What are these?
Yes, sorry.
Yeah, but
I
I'm
didn't.
interested in that.
No.
What is that?
I didn't explain that. Yes, I should have changed the title. That was from I spoke about this at the previous workshop. So what happens next to an ice shelf is that from time to time, episodically, for some reason, you will suddenly have an ice-laden plume come out from under the ice shelf. And when that happens, you will get precipitation of frazzle ice upwards underneath the sea ice. And I only called it Underwater Snowstorms Do Happen because that is the title that the young man who sent me the video clip gave it. We had been arguing about whether this was episodic. He said, no, we're disturbing it. As divers, we're disturbing it. And I said, no, it happens episodically because of nature. And so he was conceding defeat.
Because I was wondering if internal waves could be a source.
They
can be very, if you have an upper layer that's 100 meters, if you have an internal wave, it could be a very strong surface current, which suddenly propagates under the ice.
I think it's not, probably not. I think that we're beyond the critical latitude.
Yeah, I'm not talking about the tide. No.
Oh, not the tide?
No.
Oh, you're talking about waves generated by something? Could be, but these,
You need the tide to generate it, yeah.
yeah. We are.
You see internal waves
Yes.
from satellite in the Arctic.
Oh, from satellite?
In the north.
I don't know. I don't do
In the north,
Antarctic.
not the
Arctic.
Arctic.
We need to ask the audience. Yeah, I don't know.
No, you don't. Okay,
Yeah.
Are
thank you.
you suggesting our structure is related? No? But
I was wondering about what was a snowstorm.
Oh yeah, sorry. We can talk about it later, but some of the audience will have heard this ad nauseum. Danny?
Danny?
Sorry, Pat, I may have misunderstood the last bit, or maybe I tuned out. So the top of the convecting region should correspond to the Rayleigh number being equal to its critical value.
Yes.
So is that the principle using to back out the permeability?
Yes.
Okay. So
And so we are just taking critical Rayleigh number equals 10.
okay, all right. So the critical permeability you get, is it consistent with the temperature and the salinity content? Because you can calculate the permeability from the salinity and the temperature, right?
You mean, oh, from the
from the law, the
from the
law
Freitag formula?
From the Freitag formula, or
Well, but we don't know the salinity.
But you've got a salinity in the critical Rayleigh number.
Oh, you mean from the, well, you mean the brine salinity from the temperature? Is that what you mean? But we don't know the solid fraction.
You don't know the solid fraction.
No,
Is there any way of finding out what the solid fraction is?
no. That would be very nice to know. But I don't think we have any way of finding out. If we had the solid fraction, we'd be in a much better position, because then we could plot our permeabilities as a function of solid fraction, and that'd be much more exciting.
Okay.
You have a question?
Can I ask about the measurements in the ocean? Because you see in the video of the experiment, you see these little plumes coming down. Do you think that's what's being detected, or do you think that's?
Oh, well, the video of it, yeah, in the ocean, you mean?
Yeah.
We don't actually see many fluctuations in the ocean. The ocean is very quiet in comparison with when the temperature probe has just gone in to the ice-water interface. And we thought that was perhaps because, you know, there will be fluctuations in the ocean, of course, but there'll be velocity fluctuations as well as temperature fluctuations, and we kind of thought maybe that cancels out. Well, it doesn't cancel out, but they're not as large as the fluctuations at the within that mushy layer. Yeah. Thank you.
One more? Yes.
I wonder, when you put those thermistor strings in the ice cover, how do you select how far apart you should put them?
Oh, good question. Yeah, usually it depends on the thing we happen to be interested in at that time. We have to be careful. Platelet ice, because of these underwater snowstorms, tends to accumulate on anything that's in the water column. So we don't want them too close together, because they would just fill up with platelet ice. But we also are most interested in what's happening at as the sea ice grows. So our standard sort of separation is to have them far apart near the top, where we know we're not going to be able to get any ice-water interface information, and then closer together further down. 10 centimeters is our standard, but there's not really a very good reason for that, other than it's not too close and not too far.
Well, I think that probably is time to stop. Thank you, Pat.